Okay, so this video is meant to go through some examples of electric potential and electric potential energy. So this first one says, what's the electric potential at a distance of 2.12 times 10 negative 10 meters from the nucleus of a hydrogen atom? Hydrogen atom the nucleus just has one proton. And then how much work is done in placing an electron at this point? So let's just start out figuring out the electric potential. So equation for electric potential is KQ over R. And K is 9 times 10 to the 9. The charge of our one proton is just 1.6 times 10 to the negative 19 coulombs. And then the distance is 2.12 times 10 to the negative 12. So 2.12 times 10 to the negative 10. And hopefully you're going to pause the video, crunch these out. Guys, I couldn't encourage you enough to practice these calculations in your own calculator, just that you know how to use your own calculator with these big numbers and small numbers. So you should calculate this out, and hopefully you're going to get 6.79 volts. The second part says how much work is done in placing an electron at this point. So remember, work is equal to a change in energy, and in this case, it's a change in electric potential energy. And it's assumed that wherever we're bringing this electron from has a voltage of 0, and now we're placing it to this point where it has a voltage of 6.79. So we're looking at Q times our change in voltage. So that's going to just be an electron. Charge of an electron is 1.6 times 10 to the negative 19. And our voltage difference would just be 6.79 volts minus 0 volts from wherever it came from. And that would be 1.087 times 10 to the negative 18 joules. Okay, next question. A 15 nanocoulomb charge particle moves from point A to point A where the electric potential is 300 volts to point B where the electric potential is negative 200. So I've got this point A here, and the voltage is 300 volts. And then I've got this point B here, and the voltage is negative 200 volts. And so the first question is, how much does the electric potential change by? That difference in electric potential is 500 volts. And then how much does the particle's electric potential energy change? Again, our change in potential energy is just equal to our charge times the change in voltage that charge is experiencing. So pretty straightforward calculation in that it's the charge of our particle, so 15 nanocoulombs, so 15 times 10 to the negative 9, times our voltage difference of 500. Pretty straightforward calculation, and when you crunch that out, you should get 7.5 times 10 to the negative 6 joules is our energy change. Okay, and last question. A proton is released from rest at the surface of a 1 centimeter diameter sphere that has been charged to positive 1,000 volts. What is the charge of the sphere? So I've got this sphere, and it has a potential of 1,000 volts at the surface, and it's asking what is the charge of the sphere. So if I just look at the equation for electric potential, it's KQ over R. And I know that this thing has an electric potential of 1,000. And so my K is 9 times 10 to the 9. I'm looking for Q. And then I know that this is at the surface of a 1 centimeter diameter. So that's my distance, so 0.01. And my Q comes out to be 1.11 times 10 to the negative 9 coulombs, or 1.11 nanicoulombs. It says, what is the proton's kinetic energy and speed when it's 10 centimeters from the sphere? So it's I've got this proton right here, and it is clearly going to get repelled. And it's saying when it's right here, what is the velocity going to be? When it is this distance of 10 centimeters from that sphere. So the way in which we need to approach that is figuring, okay, what is the difference in voltage? I know that my voltage right here is 1,000 volts, but what's the voltage right here? So we have to first do a voltage calculation where I'm looking for I'll call it voltage 2. I know the charge. The charge doesn't change. The charge is still going to be this 1.11 times 10 to the negative 9. So it's still going to be our K, 9 times 10 to the 9, times our voltage of 1.11 times 10 to the negative 9. And now I am a distance of 0.1 away. So you would calculate what that is. I'm going to leave it. Trying to leave some for you to do. So figure out what is that voltage. And then in terms of kinetic energy and speed, essentially this change in potential energy is going to become kinetic energy. So I know that I've got this QV of my proton, and that's going to become a kinetic energy. I guess it's V naught squared. So a few things that you know that the charge of a proton is 1.6 times 10 to the negative 19 coulombs. The mass of a proton, you might remember, it's on your equation sheet, but it's 1.67 times 10 to the negative 27 kilograms. You know that this thing starts from rest. And so you're essentially trying to figure out what is this kinetic energy, and then once you have that value, what is the velocity? Okay, so you are going to figure out what is this difference in voltage. We know that the initial voltage is 1000. What's the new voltage? And how does that translate into becoming a kinetic energy? Okay, so finish this one on your own at home. Run the calculations, and then we will go over the answers in class.